Greetings, calculus scholars. Today we're going to be doing skill 9, which I titled the secant line. So at the end of the day, what calculus kind of is, what some people say that calculus kind of is it's the study of the rate of change. Calculus is a study of rate of change. And when we actually, at the end of the day, think about rate of change, this is a word that you've seen since about 6th grade, slope. And what we're going to do, to kind of introduce this skill, is look at how you have looked at slope through the ages. So I want to give you a timeline of your mathematical journey and the concept of slope. So when you were in pre-algebra and they started introducing you to slope, they called slope a variable m, and they told you that slope was rise over run. So that was about pre-algebra. Maybe towards the end of pre-algebra, beginning of algebra 1, they said that slope was your change of y over change of x. This is y2 minus y1 over x2 minus x1. And then when we get to algebra 2, they may have given you an equation that was in function notation. So like maybe you had f of b minus f of a over b minus a. Maybe you've seen this equation before, but it's the type of thing where I give you a function and you plug in the starting and ending point of the function. And then at the bottom, that's just the width of your interval, or x values, so to speak. We call this equation the average rate of change. And this is where we're actually going to be starting out for things in calculus. So in calculus, we are going to be learning about what are called derivatives. But first, we study and develop from average rates of change. So that's kind of your look at slope through the ages. So I'm really looking forward to kind of building on this in the next several weeks. And one question that I think we will be answering, in pre-algebra and algebra, we took slopes of like straight lines. But how do we take, this is kind of our essential question of the unit, how do we take slopes of curves? Okay, so basically, I'm just going to put it out here graphically, what we're doing. So let's say that we are traveling on, maybe this is like a skate park ramp or something like that, and the person is right here. I'll draw a little person here on your skateboard. And we want to know, what is the slope of your skateboard at that point? So we're going to learn about this ideal later on called a tangent line. So this actually turns out to be what's called our, the slope of it is called our derivative. But for now, we're just going to learn about secant lines. And the advantage of this is we can actually use algebra to compute So just algebra. And what we'll find is that it gives us an approximation of what the slope is going to be, but not exactly, what the slope is going to be at that point. But I think it's important to kind of look at slopes of secant lines to really help us develop what that tangent line and what that derivative really is. All right, so I'm really excited about delta math, and I even played around a little bit with delta math and how they kind of present the concept of a derivative. And I actually have to say that the graphical exercises that they included really do a nice job of getting you in those graphs and you kind of playing around with those graphs and seeing, what's going on. So I'm going to assign both graphical examples and sort of the computational algebraic examples in delta math. What I'd like you to do is I kind of do some of these demonstrations that I'd like you to record those examples, either with summary or tips. So let's go open our delta right now. We are now in the definition of derivative and tangent line section. So what I'm really excited about is this average rate of change. So it tells you, here's a function, and it's telling you to start at x equals -3 and connect it with x equals -2. And you can see right there that it actually maps a line, a secant line, that you can compute the slope of. And I'm just going to zoom in. And like in the good old days of pre-algebra, you can find its rise over run. So this is going up 4 over 1. We actually get to see exactly what is going on here. So like up 4, right 1. So our slope would be 4 over 1. And that's the slope of our secant line. So I'm really kind of excited about this. It gives you your change of y, your change of x. That's going to be 4 over 1. And you get to immediately find that average rate of change. Oh, I made a little mistake here. I got a little ahead of myself. I actually misinterpreted this graph here. I should have read the scaling of the units. So they actually do play around a little bit with the scaling of the units. So you're actually increments of 2, so it's really 8 over 1. So just pay attention to the scaling of your units. I'm actually not going to fix this part of the video, because this is, I would say, will probably be the common mistake that you may make the first few times that you go around. So moral of the story, look at your units. It's like this is every 2. And we'll kind of do one correctly this next time. All right, so I got x equals 4 and x equals 8. Ooh, they really went fancy here with these units. So here's 4, and here's 8. It's a little fussy sometimes. You just have to deal with it. This one you can actually see a little easier. So we go from 0 to 40. So that's our rise. And then our run is 4. So then our slope would be 10. And that's correct. We also have a very good exercise of just looking at computing your average rate of change. So you could actually, I'm actually going to manually compute this. In the demo video, I believe they also show you how you could use like your online graphing calculator to do this too. But I want to kind of show you what's going on when you compute it manually. So what I would do here is I would find f of 1 first. That's going to be 1 squared plus 2, which is equal to 3. Then I have f of 3, which would be 3 squared plus 2, and that would be equal to 11. So this would be f of 3 minus f of 1 over 3 minus 1. So this comes from your formula of f of b minus f of a over b minus a. So average rate of change. And that's what they're asking you to do when you're doing the secant line. And then I can just use the data that I computed. So I have 11 minus 3 over 2. It's going to be 8 over 2, which is just equal to 4. So with these, find the f of the endpoints. So plug in the starting point and the ending point, substitute it into your equation, and you'll be able to get your answer right there. Okay, and then we also have an exercise that I'm going to give you where you're actually going to be exploring what's going on with secant lines graphically in the zoom in feature. So your goal here is that you want the blue dot to be as close to the yellow dot as possible. And it actually shows you, like right here, what the slope is. So it's actually doing it for you. And your goal is to get this as close as possible. And then you're going to zoom in. And you can see that you're getting like microscopically close to the slope of the actual line. And this is the ideal that we call the slope of the tangent line approaching. We're just going to go right to it. And we can actually see that it's about negative 1.2 from the slope. So I love this example because it interactively illustrates how we're going to be moving from the secant line to getting to the slope of the tangent line, which we're going to talk about next class. So please stay tuned.